Okay, this is Unit 7, Natural Selection, Lesson 72 through 74. This is the first day of Hardy-Weinberg equilibrium. When you guys hear the word equilibrium, what does that mean to you? Like, what is a synonym for something being at equilibrium, John? Same on both sides, balance perhaps. What else, Adriana? Stable. And when I hear equilibrium, it's hard to say the word equilibrium without equal. So when you have Hardy-Weinberg equilibrium, all things are really on a level playing field. Well, remember that evolution, by definition, means change over time. Hardy-Weinberg equilibrium is contradictory to evolution. In Hardy-Weinberg equilibrium, allele frequencies for a specific trait within a population will not change. Evolution means change over time. And if I'm telling you that the amount of allele or the frequency of alleles of a dominant form of a trait or recessive form of a trait will not change, this means that there will be no evolution, no change over time. That's what Hardy-Weinberg is all about. In order for there to be no evolution, you have to have 5 conditions to be met. Now, yesterday in class, we went over the 5 things that do cause evolution. In any given order, can you guys share with me what those 5 things are that do, in fact, cause evolution to occur? Tell me one, Mackenzie. Genetic drift, which is random changes to the allele frequencies. Natural selection, survival of the most biologically fit. No, we never said that one. Genetic drift, natural selection, 2 down, 3 to go. Gene flow, migration, in and out, traits in and out of a population. Mutations, permanent changes to the genetic code. One more. Non-random mating, selecting a mate based on preferable traits and rejecting potential mates that have traits that you don't like. You take the opposite of those 5, you'll stop evolution, and here they are. No mutations, no natural selection, no gene flow, no genetic drift. And what's the opposite of non-random mating? Random mating. You don't select a partner because they have traits that you like or that you find good or fit. You pick a mate just because they have a pulse. They could be like the most unfit individual in the world, but hey, there they are. You take these 5, and there will not, if these 5 conditions are met, the population will be at equilibrium. And once again, if it's at equilibrium, there's no evolution. It's stagnant, no change. It's going to stay that way. When you're doing all the word problems that you're going to be getting for next class and the class after that, you're going to hear a lot of the readings say, the following population is at Hardy-Weinberg equilibrium. That just means that these 5 conditions are in play. And you got to be 5 for 5. Now, when it comes to the Hardy-Weinberg principle and the Hardy-Weinberg equilibrium, there are 2 mathematical equations, which is why I've asked you to have your calculators with you. You will be given these equations on the AP Biology exam formula sheet. I let you use these sheets on the test, but you got to know how to use them. So the first equation is allelic frequency, the frequency of the alleles. And the equation is P plus Q equals 1.0. Now, this equation has the word frequency in it, and 1.0 is a frequency. What is 1.0 as a percentage? 100%. There's an expression in common conversation that says they're batting 1,000. Let's say Bo is playing baseball and he's had 5 at bats and he's hit the ball 5 times. We would say that he's batting 1,000. His batting average is going to look like this on the scoreboard. Now I know that's not 1,000. That's just 1.000, but it looks like 1,000, and what that simply means is 100.0%. That's what batting 1,000 means. Now, what the heck does P and Q stand for? P stands for the frequency of the dominant allele. And traditionally, historically, what symbol have we used to represent a dominant allele? A capital letter. Doesn't have to be, but traditionally that's what we use. And then Q is the frequency of the recessive allele. And what have we traditionally used to represent the recessive allele? The lowercase form of that same letter. Now, I've been at this a long time, and I've seen many kids hit a lot of dead ends. And I want to help you guys avoid those dead ends and not make the same mistakes they have. So as we go through this lesson, this class, next class, and the class after, I'm going to try to help you avoid those landmines. And here's the first one. When I write a lowercase letter, you write a lowercase letter. When I write an uppercase letter, you write an uppercase letter. Now, someone last period brought up a great point. And I got to tell all my morning classes this. She said, Mr. Thorson, what if you're dealing with a codominant trait and there's not a dominant form and a recessive form? It's a great question. So in that case, the dominant allele, or P, can also mean allele number 1. That's it, just allele 1. And the frequency of the Q is the frequency of the recessive allele, or allele number 2. What she was getting at is, what if you're dealing with like codominance, where, pay attention to this, guys. Let's say this is, you don't need to write this down. Let's say this is a blue flower. That's a purple flower. And this is a blue-purple flower. B and P are not dominant and recessive. They're codominant. Well, then you could just call B allele 1, P allele 2. I'll have to bring that up for my morning classes tomorrow. Now, the other equation is the genotypic frequency. And that equation is P squared plus 2PQ plus Q squared equals 1.0. Lowercase p, lowercase q. Don't be doing capitals when I'm not doing them. P squared is the frequency of homozygous dominance. And when I say homozygous dominant, what kind of alleles make that genotype? 2 dominant alleles. 2PQ is the frequency of heterozygous. And what 2 alleles form a heterozygous genotype? A dominant allele and what else? A recessive allele. And then Q squared is the frequency of homozygous recessive. And what alleles represent a homozygous recessive genotype? 2 recessives. There you go. Now, in the event that you were doing something that's codominant, P squared can just be two copies of allele 1, and Q squared can be two copies of allele 2. When we come up to a problem, which I really hope we do on codominance, I'll show you what I mean by that if you're still a little unsure. But it mainly deals with codominant traits like blood type or flower color or something like that. All right. So, with that all being said, I'd like to get into your first example problem. Kind of stretch the legs a little bit. So, please have your calculators out. And as we do this first problem, I'm going to help you avoid a lot of these landmines that years of students before you have run over. And I've come to learn where their common misconceptions are. I want to help you avoid them. So if you are a little, I know this stuff can be a little unfamiliar and not fun at first, ask questions. Advocate for yourself. Here we go. In a population of 17 students.
Teachers and students, please excuse the interruption. We do have some impending inclement weather on the horizon.
Okay, so due to bad weather while I'm recording this video, I'm going to have to cut this video short, but I will make part 2 of this video picking up right where this video left off. So I'm going to end this video for now. Part 2 will be next.